Hi guys, welcome to the second part of our video concerning section 9.5, all about electronegativity and bond polarity. In this video, I'm going to continue where I left off, and I'm going to start talking about molecular polarity. So when we consider molecular polarity, we're going to need to consider how all of the bonds in the molecule will affect the overall electron distribution of our molecule. Remember, of course, polar bonds and polar molecules having an unsymmetrical distribution of electrons, where nonpolar will have a symmetrical distribution of electrons. So first, I'm going to draw my Lewis dot structure for CCl4, carbon tetrachloride, also known as chloroform. The carbon in the middle, and our 4 chlorines going in each direction. And cool, good stuff. Now, we can look up the difference between carbon and chlorine in our electronegativity tables, which are part of your reference table. And I actually recommend that you do that. You'll find that chlorine has an electronegativity value of 3.2, where carbon has an electronegativity of 2.6. So we'll say 2.6, 3.2. So they do have some difference in electronegativity. And the result is that they have a polar bond. So we'll say the C to Cl bond is polar. Okay, so cool. Now I'm going to quickly annotate this, right? We know our more electronegative element will get a little bit negative. So I'm going to say this one's delta negative. Well, the same could be true of this bond to chlorine here, and this bond to chlorine here, and our 4th bond to chlorine. And hopefully you guys are seeing that. Interesting. Each of the bonds, and all of these bonds are identical, and they're all pointed away from each other. All of these bonds are pointing in opposite ways. So if I draw the overall polarity for this, if I think about drawing these as one thing, I'm going to erase my electronegativity values just for the sake of space. I'm going to draw my arrows showing where the electrons would go. And so they'd be pulled from carbon to chlorine here. They'd be pulled from carbon to chlorine here. They'd be pulled from carbon to chlorine here. And they'd be pulled from carbon to chlorine here. And imagine, if you imagine for a second a tug of war, well, if you have 4 people pulling on a rope in opposite directions with the equal strength, they are going to cancel each other out. So our key to look for our CCl4 here is that because the bonds pull in opposite directions with equal force, the polarity cancels out. So the polarity cancels out, which is kind of cool to think about, right? The electrons are not on one side of this molecule. They are evenly distributed around the exterior of this molecule. So there isn't a positive side and a negative side. It's all evenly distributed. Well, when we have an even distribution, this results in a nonpolar molecule. Nonpolar molecule, which is fascinating. And I'm actually gonna change the example that I'm gonna work with. I said HCl. Well, let's compare that to something like CHCl3, right? So it's going to have 3 chlorines and a hydrogen. So I'll draw that quickly. Again, we have our central carbon. I'll put the H going down, and then we have our chlorines going to each side. Again, I recommend that you take a look at the reference table and see if you can identify the electronegativity value for your hydrogen. It is 2.2. So carbon was 2.6, 3.2, and 2.2 for our electronegativity differences. And so when we think about the C to Cl bond, that, of course, was polar. And it is effectively polar because if you think back to the last video, it has got an electronegativity difference of 0.6. So we count that as a polar covalent bond. Well, I'm going to draw those polar covalent bonds just like I did in the last example. So we have our electrons being pulled that way, and that way. And you can see the left and right arrows are facing opposite from one another. Maybe they cancel out. Of course, this is a 3-dimensional structure, so it's not actually going to be a perfect cancellation of these two things. It's going to be some vector math. And if you're curious about how that actually works and how this would really work, ask me during office hours. I can explain it. It is just as effective, though, for you to consider that these two bonds are pointing directly away from each other and would cancel. However, my electronegativity difference for my H to C bond is only 0.4, and therefore we would consider that to be a nonpolar bond. So for this molecule, because there is a lack of symmetry, and because this bottom hydrogen here is not a polar bond, overall, my molecule, in green, I'll draw the overall molecule's polarity. So the overall molecule is, in fact, polar. And we could say because the bonds are not symmetrical, they don't cancel, and the molecule is polar. So when we're considering an entire molecule, it's got two conditions, right? So here it is, and please make sure you write this down. Molecules will only be polar if they contain polar bonds, and I'm going to highlight, their symmetry does not cancel out the polarity of the molecule. So not only do they have to have polar bonds, their shape basically has to be unsymmetrical. Here's a quick hint, right? Molecules with essential atoms that have lone pairs, not long pairs, but lone pairs, are typically polar if the molecule contains polar bonds, or if the molecule is not symmetrical around the central atom. So you can see that in our example on the right. When I have a hydrogen here, there is no longer symmetry and the molecular polarity doesn't cancel out. So the entire molecule was in fact polar. All right, so why should we care about this? Well, there's really one important property that we're going to talk about now, and we will talk about the remaining important properties in chapter 13. And so the key property you need to know is that like dissolves like. And so that means polar solvents can dissolve polar compounds. Above, I can predict that CHCl3 will dissolve in water, and CCl4 will not dissolve in water, because water is a polar compound and it can only dissolve polar compounds like our CHCl3. Likewise, nonpolar solvents can dissolve nonpolar solvents. So I might expect my CCl4 to be able to dissolve in some kind of oil or some other nonpolar substance. All right, guys, that's all I have for this video. Thank you guys for listening, and I'll see you in the next one. Bye, guys.